Alright guys, welcome back to this video. In this one we're going to talk about the ratio test. And the ratio test helps us with some gnarly looking series. So a lot of people have been asking about some complicated series. So if you have the series like 2 to the n times n cubed over n factorial, and you might ask, does this converge or does this diverge? Well, I think that's a fair question, but that's an ugly series that's not really suited for any of the tests we know so far. And for that, we're going to use the ratio test. The ratio test is very powerful. You could think of this as kind of like the Ghostbusters of tests, right? You think about Ghostbusters. What's the theme song? Who are you going to call Ghostbusters? Who are you going to call ratio test? So you're basically going to use this if you don't know what else to use. It's a good catch-all. The math can get a little gnarly, which is why you probably don't want to start here if it's like a p-series or geometric series or something. But it's something that always will work out pretty nicely. And well, not always, but in most cases will. And it is great if you have exponents, especially if you have multiple exponents. But it is particularly great with factorial. So if you ever see a factorial in your problem with a series, just jump straight to the ratio test, and I'll tell you about convergence versus divergence. Okay, so that's it. That's the ratio test, the name of it, how it's used. Ghostbusters, you call it like the Darth Vader, whatever. But let's go ahead and talk about what it is. The ratio test says this. For a series, a sub n, if you take the limit as n goes to infinity of the ratio of terms, so an plus 1 over a sub n, if you take that limit and that limit is greater than 1, what that tells you is that that series diverges. If that limit is smaller than 1, that tells you that this series converges. And it actually converges absolutely, which is kind of cool. In all cases, it'll be an absolute convergence if this limit is less than 1. And if the limit is equal to 1, this is inconclusive. And basically what you should do is try another test. So if you do the ratio test and you get a value of 1, you kind of screwed up. Just do another test. Usually it's like a p-series or something. So let's think about what this means. This is like a limit as n goes to infinity. This is just a ratio of terms. So it's saying as we go to infinity, what is the ratio of the n plus 1th term to the one that comes before it? And if that limit is greater than 1, that's telling you that the term on top is bigger than the term below. So that means the terms are getting bigger, so it's not gonna go to 0. If this limit is less than 1, it tells you it's converging because they're getting smaller at a ratio, right? Each term is significantly less than the one that comes before it if you have a fraction less than 1. Okay, so that's what's going on. That's how you take this limit. Let's go ahead and do some example problems so we can see what this looks like and work through some of the algebra. And there's going to be a lot of algebra in this video, so I'm going to recommend that if you get stuck on the algebra, feel free to just pause the video, try and work it out yourself, and then if you need to rewind, that's okay. But I would recommend you actually work the algebra out yourself. So once I set up the limit, try and simplify it yourself and see what you can get to. Okay, so what we're going to do, let's say we have the series 3 to the n divided by n cubed. Okay, we see 2 exponents, so that's a good point to use the ratio test. So let's go ahead and set up the limit. So when we set up the limit, so we're saying we're going to take the limit as n goes to infinity of an plus 1 over a sub n. So what that means is you're just going to plug in n plus 1 on top. So you're going to replace all the n's with n plus 1s. So that's saying you're taking the limit n goes to infinity of, so this is like your a sub n. So if you want to do a sub n plus 1, you just replace the n's with n plus 1s. Okay, so that's going to be 3 to the n plus 1 divided by n plus 1 to the 3rd power. And I'm dividing by, and this a sub n is just the original term of the series, so nothing there. Okay, and this is all in absolute value. I know it gets a little onerous, but do write the limit and the absolute value in each step. They're looking for that on the AP test. If you don't do that, they will take off points if you're not consistent with that. Okay, so what we're going to do is we're going to flip the fraction at this point. Okay. So when I flip this fraction, I'm going to get limit n goes to infinity of 3 to the n plus 1 over n plus 1 cubed times n cubed over 3 to the n. Okay, now what I want you to do is we're going to try and line up terms. we're going to try and line up like terms. And what I mean by that is we're going to try and line up like the 3 to the n with the 3 to the n. We're going to try and line up, for example, this n cubed with this n plus 1 cubed. And we can do this, right? Because like 2/3 times, 3 over 7 is the same as doing 2 over 7 times 3 over 3. That's just how fractions work, right? You multiply top, multiply the bottom, so you can switch the order around. So what I'm going to do now is after I flip the fraction, now I'm just going to try and simplify. So I'm going to turn this into the limit n goes to infinity of. So I'm going to put the like terms together here. So that's going to give me 3 to the n plus 1 over 3 to the n times n cubed over n plus 1 in parentheses all cubed. Okay, now you're going to notice a cool simplification here. The 3 to the n plus 1, we know that's equal to 3 to the n times 3 to the 1. So that becomes 3 to the n times 3 to the 1, or just 3, over 3 to the n. And then one trick that we're going to try and do is we're going to combine these into one exponent. So when you have, for example, like n cubed over n plus 1 cubed, like in terms of math, right, that's the same as doing n over n plus 1 and just cubing the whole thing. With a fraction, you cube the top, you cube the bottom. So I'm going to turn that into n over n plus 1 cubed. Okay, now all the cool kids in here notice that the 3 to the n canceled. So what you have is after simplifying and combining those terms, you just have 3 times n over n plus 1 to the third power. Now we're ready. We've done all the simplification that we can possibly do. Now we're going to take the limit. And again, we don't take the limit until after we've simplified and canceled like terms as much as possible. So when we take this limit, this is going to be 3 to, okay, well, look, I mean here, you kind of want to move the limit inside. So you're going to move the limit inside to the n part. So it's like limit n goes to infinity of n over n plus 1. So, I mean, you can L'Hopital it or leading terms. It's just 1 over 1. So this just goes to 3 times 1 over 1 cubed, which is just going to end up being 3. Okay. Now, that was our limit, so let's go back and compare that to our answer, or our theorem here. If the limit was greater than 1, that tells me the series diverges. Okay, so we're good. So that means that the series is going to diverge. So again, that tells us that this series diverged because of the ratio test. So let's walk through that again. We set up a limit of these terms. This is like plugging in the f of n plus 1. This is like your original f of n on the bottom. We put the like terms together here, the 3's and the n cubes. We put those into one exponent, and then we just simplified, and then the last step was to take the limit. Okay, and that told us about convergence. So this took a little while, and algebra is a little hairy, but that's how we do these problems. So I want to show you, I think, 2 more where we can go over some various tricks of the trade that are going to come up. So again, we're going to ask on the next 2 examples, does this converge or does this diverge? And let's look at the series -1 to the n times 2 to the n plus 1 divided by n factorial. By the way, 0 factorial is actually 1 if you're curious. We can talk about why that is in class if you are curious about that. But let's go ahead. As soon as you see a factorial, that should tell you that the ratio test is going to be the way we want to figure this out. So let's go ahead and set this up. So I'm going to take, that's my a sub n, so I'm going to take the limit n goes to infinity, absolute value. So I have 3 n's to replace here, right? I have 1 here, 1 here, 1 here, and I need to replace all those. So that's going to be -1 to the n plus 1 times 2 to the n plus 1 plus 1, so n plus 2, divided by n plus 1 factorial. And I'm dividing this whole thing by -1 to the n, just the original terms. I'm just going to rewrite this. Okay. So now again, I want to flip the fraction, and I'm just going to, like usually when I do these problems, I just kind of flip the fraction on the first step and bottom and multiply. So flip the bottom fraction, and then we multiply. So this is going to be a limit. So we have absolute value -1 to the n plus 1 times 2 to the n plus 2, distribute there, divided by n plus 1 factorial times n factorial over -1 to the n times 2 to the n plus 1. Okay, so a couple things here. If we take the absolute value, we talked about this in the alternating video, if you take the absolute value of a -1 to the n, that cancels it out, right? Because like the absolute value 1 and -1 is the same thing. So you can get that canceled because of the absolute value signs. So then if I line up my terms together, this is just going to be a limit n goes to infinity of 2 to the n plus 2 over 2 to the n plus 1 times n factorial over n plus 1 factorial. Okay, so the cool kids notice, of course, that we can simplify the first part here, but we can also simplify the second one. So this is 2 to the n times 2 squared over 2 to the n times 2 to the 1. Those will cancel. The trick I want to remind you, we did in class a little while ago, n plus 1 factorial, just go down by 1. So that's the same as n plus 1 times n factorial. If you needed to do like n plus 3 factorial, that's the same as n plus 3 times go down by 1, n plus 2 factorial. Because we know, 6 factorial is just 6 times 5 factorial. 10 factorial is just 10 times 9 factorial. You just go down by 1. Anyway, this is going to happen every single time you do the ratio test with a factorial with the bigger one. So this is just times an n factorial, and rewrite the bottom as n plus 1 times n factorial. Okay, now, here's the beauty of the ratio test, because when you do that, these terms cancel every single time. And that's why the ratio test is beautiful with factorials. So you're just going to end up taking a limit n goes to infinity of 4 over 2 times 1 over n plus 1. Okay, so when you finally have done all your simplification and canceling, then it's time to take the limit. So you're going to get 2 times 1 over infinity, which is 0. Last thing I checked, 0 is less than 1, so this series converges. Okay. So that's just how you deal with the factorial, how you deal with the negative 1 to the n. So that's actually pretty sweet that these just like cancel out, and that'll always happen with a negative 1 to the n in absolute values. That's kind of cool. Okay, so that's the ratio test. Let me show you just kind of a messy one last example, and then that'll be the end of this video, and we can go eat some bagels. So let's take the sum from 1 to infinity of 5 times square root of n times 2 to the 2n divided by n minus 1 factorial. Yuck. Now again, when you look at this, you see the factorial immediately. You want to think about the ratio test, which is always a good idea because we have a couple exponents too. Okay, so this is my a sub n. So let's set this up. So when I do this, I'm going to take the limit n goes to infinity of absolute value, an plus 1 over a sub n. So again, we have to plug in the n plus 1 in 3 cases. Okay, so when I take that limit, the an plus 1 is going to be, let's see, 5 times square root n plus 1 times 2 to the 2 parentheses n plus 1. Going to have to distribute that there. Divided by n plus 1 minus 1 factorial. And then I'm just going to go ahead and flip the fraction on the bottom and multiply right away. So that's just n minus 1 factorial divided by 5 times square root of n times 2 to the 2n. Okay. Now remember, everything is canceling here, or everything is multiplied here, so we can just cancel the 5s right away, so that's cute. The constant just goes away, which is good. I mean, you just pull it out in front too, so it's whatever. All right, so now again, I want to line up my like terms. I want to make sure my like terms are together. So I'm going to put the root n plus 1 and match that up with the root n here, okay? And n minus 1 factorial, I'm going to match that up with n, oh, that actually cancels, which is nice. That's just n factorial. And then when I have 2 to the 2n plus 1, I distribute that out. So that's 2 to the 2n plus 2. And on the bottom, I have 2 to the 2n. Okay. Now, just like we did on the first problem with the cubed, I want to combine this into 1. And I would generally keep the factorial separate from the square root stuff. But combine this into one problem here. This is just going to be square root of n plus 1 over n. Okay. And then with the factorials, again, you want to mess with the big one. Like whichever factorial is biggest, that's one you want to change. So n factorial is equal to n times, and go down by 1 to the next number. Just subtract 1 to get to n minus 1. So that means that on the bottom here, we're going to change this into n times n minus 1 factorial. And here, again, let's split this up. So that's times 2 to the 2n times 2 squared. One of the common mistakes I see, people forget to distribute out this 2. They just put 2n plus 1 without doing it 2 times the whole n plus 1, so you got to distribute. All right, so then that's over the 2 to the 2n. All right, now we're going to have some cancellation. Bam, bam, bam. So we can rewrite this as the limit n goes to infinity of square root n plus 1 over n times 1 over n, we still have that on the bottom, times 4. All right, and then now when you take a limit on something messy like this, just take the limit of each part. Okay, and the same trick is going to happen anytime you have an exponent on here. It's going to end up being like, you move the limit inside, you take the square root of the limit of n plus 1 over n, it's just going to go to 1 over 1. And that's going to happen like almost every single time you have, something you have like an n plus 1 over n raised to some power. It's just always going to be 1 over 1 to that power. So this is going to turn out to be, okay, that's just 1 over 1 times 1 over infinity, which is 0, times 4. So this just ends up being 0. 0, of course, is less than 1, so this series does converge. Okay, so that's the ratio test. It's a little bit messy algebraically. Make sure you practice that. The more you do this, the more comfortable you're going to get with that. And cool, bring some questions on this to class, and let's go eat some bagels. May you have lots of cream cheese, and I'll see you guys soon.